Okay, so hi everyone. Thanks everyone for joining. So today it's my pleasure to invite Mayur and Naik, who's a faculty here at Penn working on differentiable reasoning. So today he's going to be talking about some of that work. So yeah, I just hand it over to you, Mayur.
Great. Thanks, Osbert. Hi, everyone. Um, so this is, let me begin sharing, presenting. So this is joint work with several folks, two of my PhD students who are here on this call to answer any hard questions that might come up. So Gianni and Ziang, but also folks at Georgia Tech who work in machine learning, and my former student, Shuji. So to set the context for this talk, here are some of the kinds of applications that we'd like to target. So the first one here is Q&A using natural language. And you can see here that there's a passage given and there's a question asked about the passage. And then there's an answer. So the goal is to have a system that can take the passage and the question and produce the answer that you see here. Another that many of you might be familiar with is autonomous driving systems, where as each frame is arriving in real time, you might want to do certain processing either spatially within this frame. So for example, identifying objects and relationships between them, or temporally across frames, tracking the same object across different frames and so on. There are many others. One which we see a lot in the news is fact checking. And I've shown an example over here where there's a claim and you might want to refer to other sources, either in the news or say on Wikipedia, to check how true that claim is. Visual Q&A is another example where this time, instead of giving a passage, as you saw in natural language Q&A, I've given an image here. And there's a question in natural language about the image, such as, is the bowl to the right of the green apple? Yes or no? And lastly, yet another application here is common sense reasoning. You might have, for example, questions about images, but that require going to common sense knowledge, which is beyond what is contained in that image. Okay. So for example, in the first image there, you see a fire hydrant and it says what sort of vehicle uses it. And the answer would be a fire truck, even though you don't see a fire truck at all in this image. So what you see is common in all of these applications is a combination of low-level perception. So you have to reason about pixel data, such as images or ambiguous natural language sentences. And you have to also do some high-level reasoning. For example, in the natural language Q&A, you even see numeric reasoning going on. But even in all of the rest, there is logical reasoning that is happening. And what I'm going to focus on in this talk is just one application as a proof of concept. And that is what is called visual question answering with common sense knowledge. So it's combining the last two applications that I showed earlier, just visual Q&A and common sense reasoning. Okay. So let's see an example here. So since this is visual Q&A, there's an image which is given of these two giraffes. And the question being asked is identify the tall animal on the left. And the answer, of course, is giraffe. But when we give this answer, you see that information such as the animal itself is not there in this image. If, for example, you used a deep neural net from computer vision, it would label this image with objects such as tree and giraffe. But normally it wouldn't label it with objects such as animal. Okay, this is where common sense knowledge comes in. We know that a giraffe is an animal, right? And while this is a fairly easy question here, where we did only one hop of reasoning in going from giraffe to an animal, you can imagine multi-hop reasoning where you might have to take a series of steps of logical reasoning in order to come back and answer this question correctly. This is a very well-studied problem in AI. In fact, I'm listing only the more recent works here. And with this example, I'm going to explain some of the columns that you see here. So in order to solve this problem, it is accepted that at the very least, we need a higher level representation of the image, right? Rather than just the pixels, you might want what is called a scene graph. So scene graph is simply a graphical representation of the high level concepts in the image. So for example, you might see here that there are objects O2, O5, and O12 in bounding boxes that have certain attributes and relationships with other objects. So for example, the object O12 has the name, which is giraffe, or it might be to the left of object O2, which is another giraffe, and so on. Okay. In practice, this is a very dense graph. In fact, it's typically a complete graph because as we will see later, it's a neural net which will take you from the pixels to this graph representation. And so every object is a giraffe with some probability, including the tree objects that you see here, and so on. Okay. So this notion of having a scene graph along with each image goes all the way back to the visual genome, which used crowdsourcing to annotate a lot of images with accurate scene graphs. Okay. In fact, this is so old that you don't even see it in this list of works I've cited here. But that's not the only thing that we might think of as useful in answering this question. We might want to have a logic representation of the question that is asked. So what I'm showing you here is in a language called datalog, which I'll explain more later in this talk. I can write this question very precisely as a logical formula. And so we call that the structured representation or the functional program. Okay. And this began with the Clever data set that many of you might be familiar with. So you see, that's the first time a check appears here. And I've cited an example, in fact, the one where we picked the data from, which is GQA from Stanford. And
is there also a background knowledge base here? Because like if you think about the animal fact, that still doesn't show up in the scene graph, right? So
great point. That was my next thing. Yes, so thanks. So before I go to that, the functional program, the reason you might need it is again to test different amounts of different complexities of questions. Okay, so once you go to a logical representation, you have more freedom to construct much more complex queries. Okay, and along with the ground truth answers. And as Ospert mentioned, in more recent works, what you start seeing is increasingly the use of a knowledge graph to represent common sense knowledge. So here, for example, is a graph where you can see that a giraffe is a mammal and a mammal is an animal, right? And now, along with the knowledge graph, we can further control the amount of difficulty of this problem. For example, you can require, you can have questions that require multiple hops of reasoning in the knowledge graph. And I'll show you in our experiments how we can have single, multiple, or many levels of reasoning because of having such a knowledge graph. Okay. So now that I've motivated a particular application, let me tell what we are here to achieve. So we have two goals. First is to develop a framework for learning and inference in these kinds of tasks. These are tasks that require combining low-level perception with high-level reasoning. And more specifically, we set out to achieve 4 goals. The first is expressiveness. So as I said, we'd like to support multi-hop reasoning in a knowledge graph. And I'll be more precise about this later on in terms of concepts such as recursive queries. We'd also, of course, like to scale. What that means is we'd like to handle large real-world data with noise. So for example, images with pixels, as opposed to, say, synthetic data. We'd like to be end-to-end differentiable. So that is something that is needed in order to be data efficient, to learn from a few labels and so on. And lastly, we'd like to be this framework to be interpretable. So it should be able to provide explanations. Okay. And our second goal is to develop this framework guided by one task that is considered challenging enough, and that is VQA, visual question answering with common sense knowledge. But we do hope to eventually use this framework for many of the other applications that I mentioned, although they would require significant extensions, for example, to handle numeric reasoning and so on. So certainly we are not the first to do this. This has been one of the long-standing goals in AI to combine perception and reasoning. And there's a spectrum of approaches depending on how much of the reasoning is done using logic. So you see that on the right, versus how much it is done using deep neural nets, okay, which you see on the left. And let us see these 4 goals that we have and how these approaches perform with respect to those goals. So in logic-based approaches, we typically, we clearly have interpretability, and we can build very expressive logics, and we can even make them scale with efficient solvers. But typically they are not easy to differentiate end to end. On the other hand, neural approaches are great at scaling to large real-world data with noise, and they're differentiable, but they have problems with expressiveness and interpretability. And as I mentioned, the others
Mayur, can I ask a question? Like, in what sense do you say neural networks are not expressive? I mean, at the end of the day, neural networks are Turing complete and data log is not, right?
Yes. So what I meant here was that if you go back to the VQA with common sense knowledge problem, right? This particular work, neural modular networks, has to train a separate neural net for each concept. So for example, relationships between objects. Okay. Let me pause and see if my students have a better answer to that. Gianni or Zian, would you like to add anything?
Yes, of course. Although neural networks are Turing complete, but in the current setup that the neural network approaches performs the best in the field is basically the neural modular networks, and that they adopt an approach that for each kind of functions, that is, for example, identify the attribute, identify the names, and identify the relationship between 2 different objects. According to these DSL, they designed a specific way to manipulate all of the network's output to generate the final answers. So this is what we mean by the expressiveness is limited in terms of the neural-based method.
Thanks, Gianni. Another way to look at it, Ishil, is that it is not, say, compositional. Okay, so as I'll show you later, we can add arbitrarily new rules that as they arise, but we cannot do that as easily in a neural approach. Okay, so we can now see here other approaches that come closer and closer to the center. So for example, deep problog extends prolog with probabilistic reasoning, and it is also differentiable, but it unfortunately doesn't scale to real world data. I'll show numbers later. What we'd like to propose is something which has an even better, strikes an even better trade-off between the neural-based and the logic-based components. Okay, so this is our goal, and I'll show you and hopefully convince you that we have made a lot of progress compared to everything else you see on this screen along these four objectives. Okay. So as Ishil mentioned, data log is not even Turing complete, but this is precisely why we get a lot of benefits in return, and I'm going to state those more precisely over here. Okay. So for the reasoning part in these tasks, we might ask what logic to use, right? And the obvious ones that come to mind is at one extreme, something which is Turing complete, and that is, for example, the Prolog language. The other extreme is just relational algebra. So for those of you who are not familiar with it, you can think of SQL. Okay, so the relational database programming language. And we chose Datalog because it extends SQL with recursion. Now, what are some of the interesting properties of Datalog? So first is it is truly declarative. So it is rule-based. And I'll talk about what benefits we get from that shortly. As I mentioned, it is quite expressive. You can even write recursive queries. Third is it is efficient to evaluate, and it guarantees termination. And this has implications, for example, on being differentiable. Since in Prolog, you can create programs that don't terminate. You don't actually even know the loss until the program has terminated. And so that poses problems for differentiability. And lastly, in Datalog, you can get also proof trees of provenance information, which serves as explanations if you want them. So the declarative aspect and the fact that it supports recursive queries is what gives us the expressiveness that we'd like. Remember, expressive is a fairly vague term here. It includes not just that we can write recursive queries, but even that we can compose, say, a knowledge graph with a scene graph in a single logic program, right? So that the declarative aspect comes into play and still guarantees termination and so on. So the efficient evaluation of Datalog, there are many open source and commercial solvers which can be leveraged to scale to real world data and for getting differentiability. And lastly, provenance information is something that we use not just for interpretability, but also for making Datalog differentiable. So here's an overview of the system we have built. So remember that we're trying to solve tasks that involve low-level perception from sources of data, such as images, audio and video, natural language text, that goes through deep neural nets for vision or natural language processing. And on the other hand, we want to do high-level reasoning. Right, so we can take the neural outputs and they become the input facts with probabilities for our reasoning component. And the reasoning component can also take a logic program, and I've shown some rules here, which I'll describe in more detail later. And now it can execute this program, this logic program on these probabilistic inputs and produce proof trees of the form you see here. And you can take the result and differentiate the loss in order to better train this neural network in a manner that is data efficient and generalizes better and so on. Okay. Any questions so far?
One quick question. Are you going to go into detail about exactly how the probabilistic inputs are generated? Because if you're talking about something like a scene graph, it's not clear to me how you would exactly differentiate through the output of the scene graph.
So yes, I will. So how about this? Let me continue, and if it's not clear, you can ask.
Sure.
Okay.
So can I just ask a clarifying question here, just to make sure I understand the setup? So the idea is that the original data log rules are given, right? So you're not trying to discover those. Those are already part of your background knowledge. All you're trying to do is you're trying to differentiate over the network that recognizes the different objects composed with the inference that is happening through those known rules, correct?
Exactly.
Okay.
Okay, so those of you who are familiar with deep problog, that is, we are not too different from them. The only differences we have are we chose data log instead of prolog. And secondly, I will talk about an approximation that we do that no longer does exact probabilistic inference, but I will show you why that approximation is a good fit for tasks of this form. Okay. So here's an example data log program, which is a discrete data log program. So you have various input facts here. For example, the name relation might say that object O2 is a giraffe. Then there's another fact which says that every giraffe is a mammal and so on. And then we can even write rules with quantifiers. So here what we say is for all O, N, and N prime. So I'm going to write these quantified variables in capital letters. The way to read these rules is from right to left, and comma should be interpreted as conjunction. And the colon equals as an implication from right to left. So the way to read this rule is if an object O has name N prime and N prime is also an N, then object O also has the name N. So for example, you can apply these kinds of rules to the input facts you see above to conclude that the object O2 is not only named a giraffe, but since a giraffe is also a mammal, therefore O2 is also a mammal. Okay. And then here we'll have an output query. In this case, I want to know what all objects, let's say in my scene graph, denoted by, again, the quantified variable capital O, have the name animal. Okay. Now, in a probabilistic data log program, we have probabilities attached to the input facts. So these would, for example, come from a vision neural network, which would say, for example, that object O2 is named a giraffe with a certain probability, 0.83. The rules themselves could also be probabilistic, but this is not something that we have done in our implementation so far. So the rules are all hard constraints.
Sorry, I have a quick question. So when you're assigning probabilities to the input facts, do you assume those facts are independent, like their probability are independent random variables?
So great question. So yes, but we have another construct as well, which is, I believe, annotated disjunctions. Gianni, do you want to talk a little bit about this?
Yes. So this is a very good question. So there are two different forms of probabilistic facts we're considering. The first kind is independent from each other, such as, for example, an object can both be tall and it can be red at the same time, and they does not actually affect each other. However, on this kind of probabilistic facts you have seen, the object 2 can be giraffe or a wolf or a pig, but this object is you know that it is because it is a classification task, and it is impossible for object 2 to be all of them at the same time. So at this time, a disjunction comes in. So in this case, we actually specify a syntax for that, which is called the annotated disjunction. And there are definitely a lot of things to talk about in even in the later part that we actually does not include this talk here because like the limitations. But I'm definitely I'm happy to talk with you offline.
I see, I see. So you have this special disjunction construct to capture some dependency between the random variables, but for other types, you still assume they are kind of independent of each other. Is that correct?
Yes, it's correct.
I see. Okay.
Okay. So for those of you who might not be familiar with how data log evaluation works, so let's ignore the probabilities for now. And let's say here are the input facts that I've shown you. We might, for example, start with, we will start with the input facts, such as the fact that O2 is a giraffe, has a name giraffe, and giraffe is a mammal. Okay, we get those facts from here. And we'll apply this particular rule once. We'll instantiate O, N, and N prime with these constants you see here. And we'll obtain the conclusion that O2 is also named a mammal. We might then take another input fact here that a mammal is an animal, apply the same rule again, and now derive that O2 also is named an animal. Notice, by the way, here that this is a recursive rule, okay? So the relation name appears both on the right-hand side and the left-hand side. So this could be, for example, this is a grounded tuple, which is an answer to this query. Okay, so in general, the result is a set of grounded tuples that are true. Now, let us slightly change the input facts. Let us say that the name relation has these pairs, O2 giraffe and O2 tiger. And what we have now is two so-called proof trees or derivation trees of the same outcome that O2 is an animal. You can either follow the proof tree, which starts with O2 being a giraffe, or you can start with the proof tree where O2 is a tiger. Okay. And as we go further, as we have more and more labels in our input, in this case of animals, we might get an exponential blow up here, okay? But the crucial part is that the query outcome will not change, okay? We'll still know that the object O2 has a name animal. Okay. Now let's get back our probabilities. You might propagate them through these proof trees, as I've shown here. In each of these trees, we only see conjunction right now, but later on we'll also see disjunctions. So for example, in this particular proof tree, we might, for example, what we would do is multiply these probabilities and finally get what's called the success probability of this query. In this case, whether O2 has the name animal. Okay. So here's an example of how you might compute this success probability. The process is more involved because in general, the derivations might share sub-derivations, although here they don't. And so we can simply add them. But in general, we'll use something called weighted model counting. And there isn't much innovation we are doing there. This follows from work on deep problog by others. Okay. So our main contribution here is what to do about this exponential blow up, right? And the idea is fairly simple and remarkably effective. So we might, for example, have 100 different labels of animals, such as giraffe, tiger, horse, and so on, right? But a deep neural net, which is producing these facts, is going to have a distribution which typically looks like something like this. In this case, object O2 is a giraffe with very high probability, but then very quickly it tapers off for the other 99 labels, okay? And so this turns out to be a very nice application domain to apply approximation, right? In particular, because these other labels are unlikely, we could, for example, just keep the top two labels, giraffe and tiger in this case. Okay. And more generally, we could have a hyperparameter K, which could determine how many cases we keep at any given point. And as I'll show you shortly, K will be used not just to prune the space of input tuples, but it will be applied at every step when we apply conjunctions and disjunctions. So it will be something that always limits the number of proof trees that we are tracking. Okay. So this is the outcome if K is equal to 2. This is the outcome if K is, say, greater than 100. So in this case, there are 100, more than 100 animals, so all of them are taken care of. Okay. So coming back here, instead of this exponential blow up, now we control this expression to be up to K terms. And I'll go more into detail with how we are doing this pruning at each step. So we can view data log evaluation as simply a series of conjunctions or joins and disjunctions or unions. So an example of a conjunction here was what we just saw. We are taking a conjunction here of the name and the is-a relation, and we are deriving more facts in the name relation. And here's the example I'll use for disjunction. You can have two different rules with the same left-hand side, in this case, a unary relation called target. And you can now have different proof trees, both deriving the same target. So this is how you do unions in data log. Okay. Let us see how top K interacts with each of these constructs by means of examples. So what I've shown you at the bottom is a rule that involves a four-way join. Okay, so you see four relations on the right-hand side. I'm going to split this into two-way joins. So let's look at the first of these two-way joins. So let us say that I've already derived so far the following facts with probability 0.83. So what are these facts? They say that O2 is a giraffe with probability 0.83. And then I also know with probability 1 that giraffe is a mammal and mammal is an animal. But then I could also have in another proof tree that O2 is named a tiger. And let us say that is with probability 0.12. Now, when I take the conjunction here, well, before I do that, let me show you the other part of this rule. And let's say I'm creating a temporary relation here called intermediate, right? And here, instead of the name relation, I have the left and ATTR relations. So for example, here, the probability that O2 is to the left of O1 and O2 is a tall object is 0.92 times 0.84, which is 0.77, right? And then maybe O2 is an object that is also left to another object O3 with a certain probability, 0.85, right? Now, the way the top K approximation comes into play here is when I take the conjunction of these two results, I get these four possibilities. What are they? Well, that O2 could be a giraffe that is to the left of O1, or O2 could be a giraffe that is to the left of O3. And Similarly, two more cases, but this time instead of a giraffe, I have a tiger. Okay. And what you see here is with conjunction, you multiply these probabilities, and you see that in the one where the probability is the highest is where O2 is a giraffe and it is to the left of O1. And so if K was 2 in this case, we would omit these two proof trees that you are seeing here with 0.092 and 0.085. Okay. Disjunction is similar. I'm going to use a different example here, which you see at the bottom. In this case, let us say I have these two proof trees, one of which says that O3 is a giraffe, and another which says O3 is a tiger. And here, let us say there are two more proof trees which say O3 is a tree and O3 is a shrub. Right? And remember, we have a disjunction here. We are interested in all objects that are named animal or plant. Okay. And then disjunction here simply involves taking the ones which have the highest probability. So we have the ones, let's say, with 0.61 and 0.23 if K was 2 in this case. Right? And so all of this, by the way, has very elegant evaluation strategies using the framework of provenance semirings that has been well studied in databases in the context of data log, where you want to annotate facts that are being deduced with various kinds of annotations, which in our case are proof trees and their probabilities. Okay. So let us say once you're done with this computation, the goal next is to discard the probabilities and just keep the logic formula in terms of the input facts that were produced by the neural net. So for example, fact F1 is something that a neural net might produce, and that object O3 is a tree with a certain probability. Or in this case, F3, which is object O3, is a giraffe. But we don't put in facts here that are discrete, so that have probability 0 or 1. Okay? So these are only the input facts that come from the outputs of the neural net. And remember, I said that there could be common subtrees here in these proof trees. And so we perform differentiable weighted model counting, which carries over from work in deep problog. And then ultimately we compute the success probability for the query that we are interested in. Okay. And ultimately we gather the probabilities to get this vector here, which says, for example, this target could be a set of objects that we have organized as this vector, and for each object in that set will give a certain probability. Okay. We have done certain optimizations here that are unique to our setting. Once we do the stop K approximation, most of these gradient vectors become sparse, and so we can do interesting optimizations there. We can also parallelize across different grounded query results within a task, which dramatically speeds up the computation at both test time, but even more importantly at training time. We don't have too much time, but I think it might be a nice. Yes.
Can you just explain how do you generate the logic formula, like the name O3 tree from the neural network output?
Okay, so Gianni, do you want to take that? I think what Jocelyn is asking is how do you get name O3, tree from the neural network?
So in our case, when we're generating these facts, you can for the name generation, you can rely on a name recognition neural network that takes in the representation of the object vector and predict, okay, there are 500 different classes that you're interested in, and predict which one of them should the result falls in, and each of them should have a corresponding probability. So after that, for example, in this case, we have generated two different values. One of them is saying O3 is a tree, and the other one is saying O3 is a giraffe. Although these two things are actually cannot exist in the same world, but you can see this these two proofs as two different worlds. And by combining these two proofs, what you can go to is in the logic formula. So in this logic formula, it is actually saying the first part is saying the probability of the result target O3 is the Curie output is true whenever the fact F1 holds or the fact F3 holds. So basically, the real compilation from the proof tree and from the two proof trees into the logic formula, you can think of that as a disjunction over the conjunction of what are the facts used there. And for example, here we have some discrete facts like the F2, it is basically inside knowledge base with 1.00 probability, and that is pretty much optimized in the compilation process, saying, okay, because this is discrete, we can just throw this away. Does this answer your question?
I guess another follow-up question is like, except like name this type of construct, what can you give other example of what construct you have?
Yes, of course.
Actually, we'll go in the experimental results. Maybe that's a better time to answer that, right?
Okay, sure.
Yeah. I think I'll skip the demo. What Gianni wanted to show here is that this is blazingly fast, but I think you all well, we are running out of time, and you can see that this runs in typically a fraction of a second. Okay, for fairly for fairly large knowledge base and real world images from the visual genome. Okay, so I'll show some numbers, and for folks who want to hang around after the talk, Gianni will be happy to show a demo. Okay. I'm going to now switch to the empirical evaluation. So we looked at many of these existing data sets for VQA with common sense knowledge and did not like any of them in the current form. And the reason for this was most of them did not seem to necessarily leverage real reasoning. And I've shown some examples here. If we have multiple choice questions, then a neural net could use certain biases or do educated guesses. The same with aggregated outputs. Yet another here is language bias. If the neural net has seen enough bananas in a data set which are yellow, then it could predict the answer without actually even looking at the current image, whether the bananas are yellow or green. Okay. So we set out to develop our own data set. And this involves three parts. What are the images and the scene graphs? What is the common sense knowledge base? And what are going to be the programmatic questions and answers? Okay. So we wanted to use real world images rather than synthetic ones to test the scalability of our approach. We wanted a knowledge graph that would leverage multi-hop reasoning. And finally, we chose object identification tasks where the output is a set of objects. So we can refer to certain objects and therefore increase the chance that there will be real reasoning needed. Okay. And to answer Jocelyn's question earlier, you can now see the kinds of things we get from the scene graph here. So we used the DSL that came along with a data set called CRIC from 2019. So let me get to that here. So the CRIC data set has 3,000 knowledge triplets that we used. And these are triplets over these relations that you see here. For example, the name, the attributes, relationships, and reverse relationships. Okay. What is a relationship? It might say that a certain object is to the left of another object, right? So does that answer your question about what we get from the scene, from the vision neural net?
Yeah, I think that answered my question. Thanks.
Right. Okay. So here you see the number of attributes and relationships. Okay. So we get the scene graphs from a recent work as well, which is the GQA data set. Okay. So we got the images and scene graphs from GQA. We got the knowledge graphs from CRIC. And I think there's an interesting research question here about how, for especially folks in programming languages, which is how to take even noisier knowledge graphs, such as conceptnet.io or even Wikipedia and so on, okay? As opposed to the manual cleanup that we had to do here. We were able to easily go from this DSL to data log. You can see pretty much a one-to-one correspondence here. And I'm going to use this notation for queries of different complexity. So this is a 4-clause functional program. So we call it C4. You see, indeed, it's a 4-clause data log rule here. Okay, so we'll go from C2 all the way to C6, okay, for the complexity of our queries. So I already sort of indicated that we are expressive. I'm not going to evaluate that any further. I'm going to use these baselines here that I've shown, neural modular networks, deep problog, and data log with reinforcement learning. I'm going to evaluate 3 things: the scalability, the performance in terms of accuracy and generalizability, and how sensitive our results are to the choice of K. So let me begin with scalability. So we saw that we were not even able to train these 2 approaches on the 50,000 tasks that we created. And so we were limited to just 10,000 tasks in the case of our baseline, which is data log RL. Here, we sampled discrete scene graphs from the probabilistic scene graph produced by the vision neural net. We run the data log program, as Armando mentioned, the logic rules in a discrete setting, but we don't allow it to be differentiable. So therefore, it's not feasible to train on too many tasks. In deep problog, we were not even able to go that far. So we simply used the pre-trained vision models. And we also only tested on 1,000 tasks rather than 5,000 tasks that we had planned for Scallop evaluation. So what you see here is as we go to more and more complex queries from 2-clause all the way to 6-clause, deep problog times out more and more often. The timeout, I believe, is 10 seconds per task here. Okay. So let's move on to accuracy. So now that we have convinced ourselves that data log RL and deep problog don't even scale well, so the only state of the art we have is neural modular networks. And what we see here are 2 ways to look at the accuracy results. So we are training on 50,000 tasks from C all. So these are queries of complexity 2 clauses all the way to 6. And we are testing on 5,000 tasks, 1,000 each for each of the 5 clause lengths. And what we see on the left is the accuracy of Scallop is much higher than that of neural modular networks. But also on the right-hand side, you see that Scallop learns much faster. So you see that its accuracy on the y-axis is much better for a given epoch on the x-axis compared to neural modular networks. Let's move on to generalizability. This time, what we asked is, can we train on tasks which have smaller, less complex queries, so of complexity 2, and then see whether our approach has learned to solve tasks of higher complexity, so C2 through C6, okay? And on the right-hand side, we fed smaller and smaller amounts of training data and asked whether our approach can generalize even with less amounts of training data. But we limited the complexity to just C2. So on the left-hand side, we varied the complexity of the tasks, but kept the training data fixed. On the right-hand side, we fixed the complexity of the task, but varied the training data. And what we see here is Scallop again outperforms both data log RL and neural modular networks, and therefore has better generalizability and data efficiency. And my last evaluation result here is the sensitivity to K, which I found very remarkable. So you see here is you would imagine that as K is increased, that we would very quickly suffer in terms of running time. But what we see here is on the right-hand side, well, we have first of all the same setup in both these plots. We are training on 10,000 tasks of query complexity C2, so 2 clause queries, and we are testing on 1,000 tasks of each of different types of complexity C2 through C6. What we observe on the left is, as expected, when you keep more and more proof trees around, you get better and better accuracy. But after a while, it tapers off. Okay, so increasing the number of proof trees and doing exact probabilistic inference is not worth it, at least for this application domain. On the other hand, what you see on the right-hand side is the running time as you go from K equal to 1 all the way to K equal to 15. It does increase, but it's barely by, say, half a second. Of course, if you were to go to K equal to 20 and so on, it would blow up. So we should have really done this experiment all the way to K equal to 100. But you would see the blow up very quickly.
Mayur, can I ask a question? So intuitively, why is top K the right approach as opposed to having a probability cutoff? So for example, if your probability distribution is uniform, then this top K trick doesn't seem like it would be effective, right?
I completely agree. And I'll let the students speak here, but this is my conclusion slide. And you see the second item here is I think we were lucky. We actually began with the application and asked what would be the best way to solve it. And in that process, we found that this top K approximation just happens to be a good fit for this data. But Gianni or Xiang, do you have anything to add here in the event that we had, say, a uniform distribution?
So what I will say is you make a very good point, and our top K application is not good for the use case when you need uniform distribution. However, one thing to remember here is there are so many machine learning tasks where the ground truth is only really a small portion of all the probabilities that it could be. So for example, by taking an scene graph, by taking an image, you can interpret it as like so many different scene graph images. However, the real ground truth is only one of them. So if you think of in this case, then you will see, okay, probably top K is a good choice because we are not concerned about so many different choices in the world as they should have very low probabilities if we train the model well. So, so this leads us to another question about, is it possible, although we know that if we have a ground truth model and the model performs really well and the top K well gives us a very accurate prediction, even though there are some probabilities at the tail part which are really low. However, this leads us to the question that given a randomly generated model, are we able to train a good model just using these top K feedbacks? And we proved it in our experiment saying, oh yes, we are able to use top K approach to train these models. So yes, does this answer your question?
So Ishil, one more thing I'd like to add here, it's a very interesting question, right? Especially if the neural model is not adequately trained to begin with. So you see here, that is why when you go from k equal to 1 to k equal to 15 on the left-hand side, you do see improvements in accuracy, okay? So I think having that extra leeway for us to get a higher k is worth it. Great. Okay, so that is.
Oh, sorry. I was just confused in terms of when you say training, are you training the underlying scene graph predictor? I just missed like what parameters you're actually training here.
I believe so, right, Gianni?
Yes, we're basically training a image to scene graph model, and we are predicting what each of the object on the image, what it could be.
And do you actually train it from scratch, or is this like what's the?
This is trained based totally on a randomly generated model and trained from scratch.
I see. Okay, thanks.
Yes.
I guess another question I'm interested in is using this type of conjunctions and this kind of logical structure. Will that make the gradient very difficult to train? Like the gradient to be too large or too small? Is the learning rate easy to tune?
I would say the learning rate is in fact very easy to tune. It is you just throw in like 4 different choices and it just automatically works there.
I see.
I was going to ask a related question, which is that, oftentimes when you're trying to do differentiability over things that are more logical in nature, differentiability is just one part of the picture, right? But it's very easy to end up with things that are differentiable, but not easy to optimize at all, that have lots of local minima and lots of nasty gradients. But it seems, given your results, that that's clearly not happening here. And so I guess sort of a follow-up to the previous question, which is, was this kind of on purpose? Or were there things that you had to do specifically to make sure that it didn't happen? Or is it sort of the nature of this particular way of doing things that you get nice gradients?
I think it is. I think it is the nature of what we are doing here. Because,
I can add on to that. So, so currently our Daylog formulation is based off from positive relational algebra. So all of the like our proof trees and our probabilities, they're formulated in a positive way. Like we don't introduce negativity in our program generation. And so I guess that is one thing that could hinder this was disjunctions, but that aligns very well with the neural architectures. So I don't think that would be a problem. But the fact that we are not introducing the negativity in the program setup is one aspect to a question. And but I do think if we are introducing more program constructs to our language, more problem will rise. But yeah, we can solve that. Does that answer your question?
Like aggregation, for example.
Yeah, I think so. So it seems like part of it is the nature of the language that you have here, that is limiting the possibilities where you could end up introducing lots of local minima.
Yeah.
Thanks.
Yeah. Okay. Great. So I believe, well, if there's any further questions, I'll be happy to take them over email. Feel free to connect with us. This was great. Thanks for all the feedback.
Yeah, thanks, Mayur, for.
Thanks. Cool stuff.
Yeah, so.
Thank you.
Bye.
Yeah, and thanks everyone for joining. So we'll see you next time. Bye.
Bye. Good to see everyone.
Bye.